I claim it's 2 o'clock, so I shall start without further ado. My name is Jason McGuiness. As you may have already heard, there's a few points of order here. I welcome questions throughout the talk, but I do reserve the right, if they get too interesting, to request that we continue it later, perhaps at the bar. I'm a contractor. I work in the City of London. I have done for many years. I work in the finance sector. It breeds a certain style of character. So, for example, I will occasionally use technical terms. A technical term is euphemism for vulgar language. That's life. Count Zero is my company. Email address. The talk is in two parts. The first part will be mainly software orientated, optimizing, flags, tweaking, blah-de-blah-de-blah. The second part will be looking a bit more generally and holistically, a bit more generally about the systems involved. So here we go. By the way, my slides tend to be full of text. I like them to stand by themselves so that you don't need to actually go to the talk or spend an hour and a half of your life watching a film of me walk around. Background. Obviously, we're about software and hardware. HFT, high frequency trading, and low latency trading. There are issues surrounding it. Mainly get the order as fast as possible to the market. Don't crash. There's a famous company called Knight Capital that in about 90 seconds managed to lose of the order of £450 million in America. It went bust and was bought out. So making sure that you don't have bugs and don't introduce bugs is really important, because you're not going to have time to stop it. And in the UK, at least, you could potentially be found personally liable for any bugs that you introduce and any serious issues that occur. And personal liability extends as far as losing your house. If you assign the house to your wife's name, because you want to try and avoid that, they'll take it anyway because they've seen that as an avoidance technique. The FCA is horrible in that respect. Of course, we've been to many talks, heard Bjarne's interesting keynotes, and last night about how fast C++ can be, and how good it can be, and how low level and close to the hardware. So clearly it's the answer. Everyone uses C++ for high-speed programming because it's good. It's a received wisdom. I'm going to look at optimization case studies. Because I'm a high-frequency trader, what we do is we squeeze it until the pips squeak. And therefore, I'm going to presume that you've done the sensible thing. Recall Amdahl and his law. 10% of your code runs 90% of your the time. Run Valgrind. Run your favorite profiler. Use that. Run it again and run it again. Once you've got bored of doing that after about a year, then maybe look at these. The other title for this talk is Nuth Amdahl, I spurn thee. Why? Because, of course, premature optimization is the root of all evil. And what I'm talking about here, if used unwisely, are premature optimizations. So, okay, I'm going to have a look at various details, those warnings out the way, health warnings, shall we say. What about the impact of the compiler, the operating system, the hardware? We're going to have a look at some performance quirks in compiler versions. Static branch prediction, the use and abuse. Why am I interested in static branch prediction? What happens is a trade arrives from some kind of computer. We don't deal with meat sacks in this. They're far too slow. So some computer generates a trade. What happens is the trade is sent to the exchange, the London Stock Exchange, Oslo Stock Exchange. And then what happens is normally you get about 10,000 cancel modifies. And then once, you get a fill. And with luck, that fill makes you money. So, static branch prediction is really useful to us because what we want to do is tell the compiler, tell the processor, no, ignore the fact it's orders and cancels and modifies that are going through all the time. We're really interested in the unlikely path of the fill. Hence, abuse. Switch statements, can they be optimized? What happens with switch statements? Of course, this is a C++ conference, and I do template metaprogramming, and according to Kevlin Henney, template metaprogramming is akin to hardcore porn in C++. So clearly we want to have a bit of fun, some extreme optimization. Now then what I'm going to do is I'm going to put it all together and see how do these micro-optimisations all fit, and do they actually make any effect in this thing called a fix to MIT/bit translator. If you work in the city, these acronyms will make sense to you. If you don't, I'll explain briefly. Fix is a terrible protocol. It's a name-value pair, all in ASCII, separated by SOHs. So you're converting from text to binary and back again all the time. It's appalling protocol. MIT is a type of binary protocol, static structs. BIT, Borsa Italia, is the flavor. Why did I choose Borsa Italia rather than Oslo, OSL? It's because B comes before O, that's why. So when I commented it out in the file, B came first. We'll have a little break. Clangers from Clang. Hee hee hee. If you find that I have it in for Clang during this talk, you might be right. And then we're going to have a look at the impact of the operating system and hardware. So this will be sort of the first bit before we have the break, and then we'll go for coffee and we'll come back for this. Right? Operating system and hardware choices. What impact do they have? And how do they affect the good old fix to MIT bit translator? So, what issues? HFT, low latency trading. You may not be in the city, apologies if you know it. Well, what are the issues? It's performance critical, very, very performance critical. Goldman's in 2012 had approximately $20 billion a day turnover on the LSE, the London Stock Exchange. Of that, 90% was automated trading, this stuff. And they were the biggest. 70, as I said, accounted for 70% of the turnover on the LSE. Today it's even bigger. So it's a lot of money. You know, within months you were talking about the gross national product of Britain, member of the G7, right? So this is a lot of money. It's not rocket science. It's not safety critical. Yes, some Deutsche traders might get a little bit miserable and jump out of a window and kill themselves, much to the inconvenience of the rest of us at nice bars, because you can't get onto the roof terrace, because these idiots jumped off, but it's not safety critical. People's lives do not matter. You might hose their pension via a pension fund, but people aren't actually going to die. Grok this well. To be truly fast is to do nothing. Nothing is faster than no exit code. By definition, just don't do it. Intraday update of IBM wants a corporate action, wants a stock split, or Apple wants to do a stock combination, recombine. So that's a market event. They get a new ISIN code, a new code for the stock, because they're removing two stocks, replacing it with one. It does not happen. You're not told that morning, that afternoon, ring, ring, Apple's going to do this. Oh dear, we better update in 5 minutes' time. Let's send an update. No, you know about it months in advance. So what happens when something goes wrong? You're out the market. Intraday restart, forget it. When I said it's not clever, it really isn't clever. All I'm doing is copying data from my input socket to my output socket, and I do a bit of transformation in the middle, as little as possible. It's not clever. It's a long mem copy, is what it is. Hence, you'll see the reason why, the motivating examples I've got. We might have some validation risk checks, as little as possible. As long as we can get around the FCA, we will. If it implies employing lawyers and pay them lots of money to get around it, we'll do it. It's not a cheap market to get into. Barcap, when Lehman's went down in 2007, 2008, bought one of the fastest and biggest trading systems in the world. It cost them $1 billion. That's the entry cost. If you want one of the biggest in the world, it's $1 billion. So it ain't cheap. Low-level control. You really, really, really are very, very interested in what happens in your hardware, where your computers are. These are co-located next to the exchange in the same room, preferably in a rack that's next to the matching engine for the exchange, preferably in the middle of the rack, because the cable length is shorter, because they commonly route the cables via the middle of the rack rather than the top or bottom, because it can make it faster. Remember, cable length is important in these matters, because if we're talking about microseconds, then cable length can be consumed in time to send a message down a cable can be the order of tens of nanoseconds. You may know some of this already. Okay, it can be very low level. So we can intimately manipulate what's happening in the hardware with my program source code. I can look at the assembly output and tune it directly from C++ statements. But of course it's nice. It's, as Bjarne said, it allows high-level abstractions. And these high-level abstractions, of course, can make it more easy to model what's going on. We've got increasingly capable libraries. Boost, of course, has been around for donkey's years, but now Boost, of course, has got atomic libraries in there, which is very nice. There's something called Frozen, which is particularly pleasant because it's a const expra unordered map, a compile time unordered map. What does that mean? No code is generated. Remember, doing nothing is fast. Of course, C++ 14 and 17 are very good because, of course, in 14, const expra was improved and you could use it in many more places. 11 was basically, it was the version 1. Just move past it, goes straight to 14. Better still 17, as we've heard already from perhaps Peter's talks, from perhaps if you went to Nico's workshop. People will talk about D, functional Java, Haskell. Garbage collection kills performance. It's just not low enough. The reality, of course, is that it's very, very easy to write something slow in C++. Ridiculously easy. But of course, there's more to it than just C++. We've got to talk about the hardware. Do we have multiple processors? One for the operating system and one for our gateway. So we'll do ISOL CPU. We'll tune the operating system. How many buses per processor? How many memory buses? You want to have a memory bus per processor so that then what I can do is I can make sure that my memory fetches. 2, the core that is dedicated, the processor that's dedicated to the gateway isn't confounded by the fact that the main CPU, somebody logged on via SSH because they want to monitor it. Networking infrastructure, as I mentioned, co-location is very important. And of course, any bugs that may exist in hardware. You saw the title, Spectre and Meltdown. Let's see what that does to us. Of course, there are a lot of details. Which operating system? We'll talk about the performance later. Not all distributions are created equal. Toolset support for rapid development. It's all well and good having a really fast system, but what happens if you want to support a new exchange, turquoise? You want toolset support, you want to be able to get that code written fast and into production to start making money, because it's all a race. Who gets there first? And trust me, there are very bright people out there who are going to get there very quickly. Configuration. C groups, ISOL CPU, performance tuning, BIOS settings. Do you enable or disable C states? What kind of cooling is available? What's the thermal dissipation? All those sorts of things. Oh dear, not all compilers or even versions are created equal. Speed test, Clang, GCC, ICC, which is faster? I'm going to focus on GCC because it's free and I've got it. C++ 14 and 17 because that's my code base basically. But also a bit of Clang will come in. And I'll look at some ICC. Basically, it's a pain in the bum to get all these compilers running and I don't have enough time in the world to, because this is all done in my spare time. So this is all IP unencumbered, what I'm telling you. Okay, hardware. This is an old AMD bulldozer. It's what I've got. It's very, very interesting because we can get to see plenty of detail. Modern processor diagrams like this, you don't get that kind of detail because it's all very IP. What is important to me here? Apart from everything, I don't care about the FPU. That can go to hell. I do care about this thing up here, the branch predictor. I do care very much about that. Obviously, the L1 data caches, obviously I care about. I care about this.
Why did you call those out, Jason? Because they're quite small to read.
Ah, right, the write coalescing cache, in order to make sure that the writes to the L2 data cache are consistent. I'm also very interested in the load store unit. Normally it's a FIFO in these processors to, again, maintain memory consistency for SMP architectures. The number of pipelines I have in my processor is very important. Do I have, notice these little arrows, I can write from an ALU, an arithmetic logic unit, which may be an adder or a shifter, I can write directly into the internal registers and pass it to an address generation unit without having to write it to my L1 data cache. This is much faster, this is nice. This is about 20 clock cycles from up there to down here, about. We'll be coming back, we'll think about this diagram a bit more later on, particularly with regards to Spectre and Meltdown, and that, the branch predictor, are caches. So, okay, very quickly and briefly, because of time, Meltdown Spector. I won't bother to read this out, but basically Meltdown, it looks at out-of-order execution, and it affects the branch predictor. It's fiddling with the branch predictor. Spectre fiddles with the cache. Billions of devices are affected. Don't be fooled, AMD is also affected as well. Okay, we're going to choose C++. C++ conference. I've already mentioned we're going to go through these. We'll warm up with performance quirks in compiler versions. Here is my example code. I'm interested in memcopy. Didn't I mention? Memcopy. So let's see what happens here. This is clearly static, internal linkage. Destination, I put the sizes in here. So this, in principle, the compiler should just write that into there in my .text section. So let's see what compilers do. We know the result. What do? Oh, they're generating code. Well, that's sad. Destination set to 0 because it was a global static, so obviously it's zeroed. So that's bad already, that it didn't just write the output into there. But GCC 447, really old one, doesn't support C++11. Immediates. These are in my instruction cache, no data cache. Instruction caches are much faster because there's no write lines. So that's good, I like that. Despite the fact it wasn't written into here, I like that. 473 in GCC, it's using the stack. See, notice, rip, source. I'm having to load it from here. This means the data cache has got to be used. Data cache, 10 clock cycle delay already. Got to fetch from main memory, 100, 400 clock cycle delay already. Desperately slow. At least, if we look at this, we've got the two move abseeks next to each other. Remember the number of pipelines I've got in my processor. The problem is if I've only got one SSE unit, it's going to stall on this abseek. So this one will have to wait until that abseek is completed. Move queues, we've probably got more move queues, more store units in our processor. Still suboptimal though. Okay, newer versions of GCC, surely they would do better. Well, GCC 4.8 to 6.3, look, it's moved the move abseek here to here. So now these move Ls that are occurring can occur at the same time as this move abseek. I'm using my pipelines more effectively. This will be faster by Mark 1 eyeball counting instructions. What's nice here, GCC 7's series, we're beginning to use VEX instructions from the AVX unit. That should be faster and also scheduled, fewer instructions, still using the stack. So that's got better, that's bad. GCC 8, extra stack accesses. But what is the real point of this? It's very unstable what's happening in the optimizer for my compiler. I can't guarantee what I'm getting. Let's look at ICC, Intel's compiler. Surely that should do the right stuff, yeah? Because Intel's got billions. They pay lots of bright people to do this, yeah? Oh, that's not very well scheduled. Newer version, oh, at least they scheduled it better, but it's still using the stack. Clang, at least it's got a stable output. Poorly scheduled, these are two are together, that should be overlapped there. Still using the stack, but at least it's stable, the output. Does it matter? You'll see lots of these graphs. Log scale. Here we have compiler versions. Why that was offset there, I have no idea. Something between GNU plot, LIX, and the PDF generator. You'll see I've got this thing called small string. I created my own small string optimized string for various perverse reasons, and it's basically got memcopy inside it. And I'll look at how fast this memcopy is running with these different compilers. We would have thought it should all be roughly similar, yes? No. Something as simple as this, you get massive difference in performance. Hang on a moment. How can I get of the order of 10 to the 15 operations per second on a 2.6 gigahertz chip? Easy, context expert. What happened is the compiler optimized it out. I like that. That's why those numbers are there. I like that. The compiler did nothing, it realized it was pointless and got rid of it. That's what I want. This I don't want. We can see that GCC 5, woefully poor performance. Consistently poor performance. We can see that it's not reliable on the test case, which has better performance. Clang beats the world here. Clang 5. Clang 6 sank. But we can't rely on the fact that Clang 6 may be poor, because, oh no, look, Clang 6 managed with small string assignments. So all I'm doing is assigning one small string optimized string to another small string optimized string. What's that? Initialized with a C string. Why is it? How? It managed to do very well here. And yet here, performance, very poor. Remember, this is a log scale, so although these look close together, in fact, there's a dramatic difference in performance. I use a log scale because otherwise this would all be a straight line and those would be very high. You cannot expect reliable performance from different compiler versions, even for similar tests. Okay, static branch predictor. I mentioned the use and abuse. Which comes first? In if bar or then else bar 2? Well, I had a look through the documentation for Intel, ARM and AMD and older architectures, and I had a chat with a few people that I know who are chip designers. There is one rule to rule them all. BTFNT, backwards taken. Those are for loops. All loops are mapped to a backwards jump. You've got a unconditional jump forward. Let no one tell you that those are slow. They are not slow at all. They cost 0 clock cycles. The instruction fetch unit and the instruction cache have that built in to know that that your IP is not IP plus 1 but IP plus a constant offset. It's not a problem. They've got built-in adders for it. This has been around for decades. But forward not taken. If then else. It's the if, it's bar 1, not else. When you write your if statements, the fall through is bar 1, not else. This is how all chip designers do it. Now, you may have heard of these operand prefixes that Intel added. They're ignored. They're not even generated anymore by compilers, and they're ignored. But when a branch predictor sees a branch it's not seen before, what it will do is it will say weakly taken or weakly not taken, depending on whether it's a forward branch or a backwards branch. A forward branch is an if statement. Why are we interested? The misprediction penalty. Because what happens is the superscalar processor, because it's superscalar, will predict that it's forward taken, if it's an if statement, and it will carry on processing the bar. And then when the condition is eventually evaluated, hopefully it's true, and if it isn't, then it'll have to roll back the results of bar 1. So that means that you've taken a stall, and the stall can be as much as 20 clock cycles. This is important. There is also another feature as well, the branch target cache. The branch target cache usually only has about 32 slots, 16 to 32 slots. It's very hard to find out because this is very proprietary information from these chip designers. They don't like telling you. Agner Fogg is a useful resource, and he has to basically experiment. So, many years ago, Builtin Expect was produced for GCC and an equivalent for Microsoft compilers. It omitted the prefixes, but now they just guide the compiler. Do they? Let's have a look. God bless Godbolt, Matt Godbolt, all hail. Let's have a look and see what GCC does. It's obviously complicated. Look, these versions and that. What happens at -00 and 01? Bar 1, bar 2. Bar 1 is the fall through. Good. What we would expect. What about 6.173? The same. Okay. What happens if we crank up the optimization levels? What happened? Just because this got negated is irrelevant. It's a forward jump. So therefore, bar 1 and 2 now is the fall through. Hang on. It just flipped. 8.1, it's stable. So what does it, so what does this mean? It means if I compile code at -03 and I statically optimize it for GCC, obviously I'm going to statically optimize it for the wrong way because they got it wrong. There's a bug report about this, by the way. You can read about the bug report, and it's quite makes interesting reading about what happened. Old Fred put in one minus in there. There's the probability of outputting bar 2 and bar 1, and it's 60% versus 40%. And what happened is when you go to O2 and O3, one minus gets put in there. Nobody knows why. Old Fred left. That's why that happened. So what happens is I've now optimized my code, spent years optimizing it for these versions of GCC that way. Now, statically, I've got it wrong. I've got to change it all. It also means, wait for it, what happens with ICC and Clang? They got it right. This means that in most versions of GCC, if I have code optimized for GCC, statically optimized fall-throughs, they'll be wrong for Clang and ICC. Okay. We have a solution for this, don't we? Builtin Expect. That'll fix it. Well, would be nice. Let's look at 485 with and without Builtin Expect. Pretty similar here, quite different. Which is faster, with or without Builtin Expect? Magenta, no Builtin Expect, faster. Significantly, materially faster. The error bars are for 4% mean average deviation. I use mean average deviation. Why? Because these are latencies. Therefore, it's a Poisson distribution. It's not symmetrical. It's not a Gaussian distribution. I can't have negative latencies because I can't break the speed of light, sadly. Therefore, the standard deviation is not an accurate measure. Mean average deviation is a better statistical measure for it. Now, okay, fine. Let's look at a newer compiler. Do we expect the same behavior? Will we get the same behavior? So I can say, okay, well, it might have messed it up, but at least I can cope with that and make the wrong choices to make it faster with that compiler. So I'll change my compiler. What happens? Oh dear. Bizarre things happen. I actually had to go, in Gen 2 you could run it with two ABIs. You could run it with ABI 11 and with ABI 09. And ABI 11 flatlined. Generated terrible code. Why? I don't know. I didn't look at the assembler. We can see here that our behavior looks roughly similar to before. But here the behavior has changed. And it's flipped round to the way we would hope it would be, that expect should make it faster. The problem is it didn't. I know specifically where this affected the code. It was in the destructor for my small string optimized string, in which I put, it is unlikely that the string will be bigger than the small size. Because that's the point of a small string optimized string, isn't it? And therefore, in the destructor to say, oh, I've got to check to see whether the size is bigger than my small size, therefore I need to delete the block I've allocated on the heap, is unlikely, I can ignore that, failed for this version of GCC. Here it succeeded. Again, we see a lack of stability in the optimizer output. I want to see stability so that when I change my compiler, when I tweak my code, reliable things happen, predictable things happen. Okay, let's look at newer versions of GCC. They were all pretty old. Maybe, surely the GCC lads, whoops, dropped a clanger there, missed the ball, we'll fix it. Completely changed again. Here, 10 to the 15, we can ignore that. It optimized it out. Here, statistically important. In this case, 6.3, I decided to stick these on a log scale because I wanted to see what happened round here. That area there, small string replace. We can still see that built-in, for a small string replace, Builtin Expect still pessimized the code. So don't expect that your likely and unlikely hash defines are going to help you. Okay, what about 7.3? 6.3 is a bit old, really, surely? You know, come on, GC8 plus 0.1, 8.2 is out. What do they do? Again, with these top figures, we can ignore them because look, 10 to the 15 operations on a 2.6 gigahertz processor. It optimized it out. I don't care. This is what I'm interested in here. Made no difference. Oh, thank the Lord. I'd rather have no difference than making it worse. Okay. What about 8.1? Oh my. Oh dear, oh dear, oh dear, oh dear, oh dear. Without Builtin Expect, GCC 8.1 optimized it out. With Builtin Expect, it didn't. The really, really worst case scenario I could ever imagine. Because here, the sweet spot was reached. Nothing was done. That's what I want to do. I want to do nothing. I want it to remove the code entirely. Here, again on a log scale so we can see a bit better what's happening around here. Still, very bad performance. Okay, what about Clang? Let's see what how Clang does. Optimizing things out, jolly good. Here, no effect. Again, that's perhaps slightly better than GCC, just being, frankly, a dog's dinner. So, flushed with that success and looking at if statements, what about switch statements? Switch statements, computed go-tos, basically. Maybe it's a computed go-to. Maybe it isn't. I wonder how they're generated. So I followed down a rabbit hole. There's a very interesting algorithm that GCC uses for generating, and most compilers appear to use for generating their switch statements, which is essentially a binary search. It doesn't use a jump table unless they're very contiguous, monotonically increasing by a fixed stride. So, fine. If a jump table's really quick, let's ignore that and let's put in different. Oh yes, and there's no static prediction for switch statements.
So no cases are more likely then.
Sorry?
So he doesn't guess any cases.
There is no, the law that the first label is more likely or default is more likely is wrong. That received wisdom is flat wrong. Forgive me, I dispel myths. So here we have an extremely complicated switch statement. You can see from my examples, of course, these are trivial examples to fit on a slide, tra-la-la-la-la. Exposition only. These were chosen by me typing on a keyboard, so they're not truly random, they're human random, okay? What was generated, if you squint and have a look at it, what you can do is, when I say it's a binary search, we look at this, we jump to 3L3. Where's L3? It's there. Or we jump to L4, which is squint here, which does a comparison, does a check, L7. So L7, so you can see hand waving, there's a kind of, it's not a similar if, it's not just a simple if chain. There's a bit of jumping around going on. But GCC, these versions, 03 generated code, no effect. GCC 8.1 ICC, unmodified. No Builtin Expect. Remember, the Builtin Expect can take an int into it. So you'd have thought what you could do with your switch statement here is say, Builtin Expect here, 30. And you'd hope it would hoist 30 somehow out of it, this case label, out of that, and put it as the statically predicted one. No, no effect at all. But Clang is affected by Builtin Expect in the way you would expect. So if I put in here, Builtin Expect I, 30, this would have been hoisted out into a condition at the beginning, an if statement at the beginning, with the else being the switch statement. That's nice. The problem is GCC and ICC are unaffected. So the problem is I don't have a stable optimization across different compilers. Yes?
To what extent do the compiler vendors have test coverage for this?
I haven't asked. It's a very, very good question. it's quite clear I would suggest they have none.
Yeah, because this seems to be like
I mean, all you do is generate the code and do a regex against the two, and is it the same or not? Yeah, and if it's different, then test failed. It's not rocket science. I mean, I've just dreamt up a test case now that could be done for this. Clearly, they don't. Otherwise, it would be, well, maybe Clang does. Maybe GCC and ICC do, and they've got it the wrong way round. Don't know. I haven't asked. So, okay, we'll hoist our statically predicted label out and do it manually. Yeah, but remember the slides I showed a little while back about if-else statements, GCC getting it the wrong way round, and the Builtin Expect being potentially a pessimization, and certainly quite good at removing const expra, stopping the compiler optimizing it out. Doesn't work, unfortunately. So, when does our break occur? I was yapping on. It's a few minutes, isn't it? 5 minutes. We can get through this in 5 minutes. Come on, it's barely any templating there. Okay, what I did is I thought, I'm going to make memcopy really fast. I'm going to make my own customized memcopy that will generate 512-bit moves, 256-bit moves, 128-bit moves, 64-bit moves, 32, 16, 8. With some template metaprogramming, aligned unroller. By the way, this file is about 2,000 lines long. So for the sake of sanity, I have omitted it. All this code is available, open source, under a very permissive license. It's LGPL. Before you all go, in horror, most people don't understand LGPL. It is not the GPL. LGPL is even more permissive than the Boost license. It is perfectly free and available for its use without let or hindrance, and IP unencumbered and non-viral. So, anyway, we've got this aligned unroller, and the basic point of the aligned unroller is you see stride. And basically what I'm doing is I'm looking at saying, can I compute whole strides here? And I'm going to generate separate blocks of code, and then we're going to mix and match assembly with lambdas, because we can. And this, see that reinterpret cast here? Trust me, that generates the appropriate SSE4 move. The appropriate move abseq for the SSE4 chip. So I am actually generating assembly using template metaprogramming and lambdas. Snip. Okay. What do I generate? If you try and cut and paste it into Godbolt, I have a separate file that I have to do that's about 3,000 lines long. So you really are abusing Matt's good efforts here. And that's what I get. It's not bad. Well, apart from the stack being used. Yeah, what happened here? We've got a mixture of the stack and an immediate. Bizarre. Oh dear. GC 8.1 fails to compile the code. So you can break compilers with this. Okay, how did Clang do? Again, a mixture of immediates and the stack. But you see, we've got my nice assembly instructions appearing, and there you can see that's 512, that's a 256, that's a 32-bit, and so on. So, and then it decided to throw in an immediate there for a laugh. I mean, why it couldn't do immediates with the lot, I have no idea. We can see potentially a performance optimization. Okay, what about ICC? Just use the stack all the time. Interestingly, it managed to schedule my code a bit better. Despite the fact I generated a fixed sequence of assembly, it actually rescheduled it and moved the move queue up here.
Isn't still this remarkably similar to the standard memcopy?
Yeah, correct. Correct. Standard memcopy is not too bad.
And about as unstable.
The problem is occasionally you see standard memcopy being called as a function.
Right.
Remember, I'm worried about clock cycles here. So a function call overhead, the call and return, is bad to me. The pushing the stack, the popping the stack are really the big killers, because that's basically 20 clock cycles I've just flushed down the drain. For the cost of maybe this, 10 clock cycles. I don't know exactly how long these take, but I do know that on the older bulldozer chip that I've got, it's unusually slow. So this is actually a pessimization on bulldozers. ICC, some more, 17 and 18. It's very unstable. What happened here? My function's called memcopyopt, by the way, just so I don't accidentally use it. I only use it judiciously. It created a function call. Does it matter? Well, it varies. Comparison. I ran my string and I replaced the memcopy in it with my optimized memcopy. Here, real pessimization in performance. Again, as I mentioned, bulldozer are unusually slow with SSE units. So therefore, they can't generate AVX2 because they don't have it. They've got AVX, so they've got 256 at best, and it's slow. Okay, what about Clang? Interestingly, not much difference. My standard, my copy, is only a bit slower. This is interesting. This would imply that my micro-optimisation, although it might look faster from the instructions, when you put it into a bit of code, makes it worse. So that means that sometimes when you think I'm going to hand massage some code and go to a great deal of sweat to try and make it faster, it may look faster in your micro benchmark and you're adding the instructions together and the instruction count and looking at the number of pipelines you've got in your processor. But the problem is when you throw it in the main code, it just generates bad code. And that's what we see here. What I suggest we do, break for coffee, and then we can go through this because it's 45 minutes and then another 45 minutes.